Couple of administrative things first. So we had a logo contest going on. I don't know if anyone in here participated in that. Anybody? Okay, we didn't get a whole lot of submissions, but I'm going to send an email out towards the end of this week about that. So watch for that if you're on the mailing list. Also, we're still looking for, we're always looking for volunteers. If you would like to give a talk about something, if you're able to host an event somewhere, if you're able to donate pizza, anything really, get in contact with us. You can email me. I'm rob@dataphilly.com. Let me know. We're always looking for people like that. There's also a data hackathon going on right now. If you check our website, you can find out more details about the place and also upcoming events. We have a lot of stuff going on this summer, so looking forward to all of that. And we're going to have our sponsor here. David's going to give a few words about Monetate really quick before we start.
All right, thanks. Hey, we're really thrilled to have DataPhilly back here for what I think is the third or fourth time, something like that. Thanks for braving the rain and SEPTA and the Schuylkill and everything else to make it out to Conshohocken and come see us. My name's David Bruson. I'm one of the founders of Monetate, and I also run our labs group. I work with Austin and all of our engineering and product teams to research a lot of the statistics and machine learning areas that are going to influence our future product. So for those of you who don't know Monetate, we power personalization for many of the world's largest brands. And that means that we help our clients understand everything they possibly can about each of their customers. Try to use that understanding to put the right experience in front of them in each moment across all of the different digital touch points where they interact with those customers. It means that we have a huge playground and a really fun one. We see about 100,000 events a second on our infrastructure. In the holidays, $1 in $3 spent in online retail is touched by Monetate. And so it means that we have a ton of data, a ton of interesting data about how brands and customers are interacting. And it lets us ask all kinds of interesting questions and dig into some new ways of thinking about the relationship between customer and brand and how experiences work differently for different people, and understand how we can help to make experiences better for customers and therefore better for the brands that we work with. If any of that sounds interesting to you, if making model-driven decisions in 9 milliseconds for every page view that might be involved with a web session sounds like fun. If dealing with hundreds of thousands of events a second, if dealing with billions of dollars in transactions, and all of the data exhaust that comes off of that sounds like fun, then come talk to any of the Monetate folks afterwards, and we'll tell you about some of the opportunities to maybe come work with us.
Other data consulting company, like, because you guys have better. Sure. I wonder, how are you guys different from other data consulting company? It's because you guys have like awesome algos, or?
So, yeah, we have Austin for one thing. Well, first of all, I would say that we're first and foremost not a data consulting company. We're really a technology provider. We provide a platform that its main purpose is to empower business users who often don't have, or I would say not just often, that almost exclusively don't have a math or statistics or data science background, to be able to make decisions every day that are informed by the work that we've done in the platform, so that they can use the data that they're collecting as a part of their interaction with their customers to make better and better decisions about the experiences that their customers have in interacting with that brand. So we're first and foremost a technology provider. We have a real-time platform that collects tons of data, that processes it analyzes it, makes decisions in a few milliseconds, and then implements those decisions in the experiences that consumers have on a bunch of digital channels, and then measures to try to understand the results. But while we do have a services group and do some significant consulting with our clients, it's not our main purpose.
Thanks, David. We really appreciate Monetate having us. Again, this is a really great space. I think this is not going to fall out. Okay, so the first talk today is going to be from Corey, who's from Penn Medicine, and he's going to be talking about Monte Carlo, not the place.
Thanks. That was pretty random, that intro. Fittingly. Okay, I'm also not supposed to show that I'm using Excel. That's embarrassing. Let's just forget that you saw that. Yeah, so that is like so random, right? You see a random dude on the street. Random thing happened to you the other day, you tell your friend, right, at the water cooler. A lot of random things going on, but we can use randomness to do a lot of really cool things, and randomness is at the heart of a lot of what we do with data, and we can harness that randomness and think about it and use computers to make our lives better and more interesting, more fun, and solve some difficult problems along the way. So first, the name. So Monte Carlo, we're talking about using randomization to solve difficult problems. Sorry, to tell the story of the name here, you have to see these three guys. So does anybody recognize these three guys? You know who that is? Yeah, they were involved with the Manhattan Project. And extra points for knowing the names. Nope, not Fermi. That's Feynman. Ulam, yes. Ulam in the middle, and John von Neumann on the right, actually, yeah. So it's Feynman on the left. So these three guys, yes, rightly, were the three horsemen of the apocalypse, as I like to think of them. So they were involved in the Manhattan Project. There they are chilling, probably at Los Alamos. And they're having these conversations about, nuclear physics, one of those. Ullman was held up in the hospital, and he was playing a bunch of solitaire, and he started to think about like, okay, well, what are the hands that I could get in solitaire? And if I could just play a whole bunch of hands in solitaire, I could kind of solve like, how often I expect these things to happen. And he also had this uncle who would always go to Monte Carlo and spend all his money gambling on the roulette wheel. And so he was thinking about these things, and he sort of realized in conjunction with these other guys, we can use this idea of having computers generate random numbers for us to solve really difficult problems. And in particular, they wanted to solve some integrals, just because guys like that want to solve integrals to help build the bomb. And there were integrals that they couldn't solve otherwise, and so they could approximate them using random numbers. So that's where Monte Carlo comes from. Use that at the bar, and it's a good trick. So the core engine of Monte Carlo is really this, generating random numbers. And all you need is something that generates a random number between 0 and 1, uniformly distributed. And from that, you can do just about anything. This thing is the workhorse. This thing is your friend. It's amazing. So there's one in Python, random number. Number's like, yeah, it's pretty random. Okay, yeah, random enough. And in case you use R, and you're on the dark side, and you're using R, you can use RUnif. That's cool. Pretty random, I guess. Yeah, pretty random. Okay. So random numbers are super cool. So let's try playing with them. Let's do a random number. Oh, yeah, okay, that's pretty random. But we can also, so we can do it with, random uniform. We can also do it with NumPy. NumPy has random.rand, which is also a uniform number between 0 and 1. So now that we have a uniform number between 0 and 1, we can do a whole bunch of cool things. We can start by flipping a coin. You might think that you need to have, a coin to flip and land on the floor to know the outcome, but all we need is a uniform random number, and we just draw one and say if it's less than 0.5, we'll call that heads, and if it's greater than 0.5, we'll call that tails. So we can do that. Oh, there's a tails. Okay, call it in the air. Tails. Oh, who earns? Okay, and then I can I'll do that with you with a trick coin. So this is a coin that lands tails most of the time. And then I'm from Canada, and in Canada, a quarter has a caribou on the one side. And also in a former life, I was kind of an ecologist. And so I called this the ecologist quarter because it lands caribou side up more often than not. So here that is. Okay, oh, tails. Ooh, that was lucky. Tails. Or no, tails is what we expect. Yeah, a bunch of tails. There's the heads. Okay, cool. So we can flip coins, and all we're using is uniform random. So that's nice. Then we can think about some other process in the world. Okay, let's think about using a device until it fails. So we can just sort of do this simple loop here. Let's just say we have some, every time you use a device, it has some probability of failure. And I actually remember when I was in high school, I was playing with my friend's Discman. So yeah, I had Discman in high school, and it had this cool clicking mechanism to open and close the case. And I was clicking it open and clicking it close. And he said to me, every time you do that, it was his Walkman or his Discman, and every time you do that, that's one less time you're going to be able to do it before it breaks. I thought, oh, okay, I'll stop messing with your Discman. Sorry, dude. But so we can think about it like that, right? Every time you do it, there's some probability that's gonna be it, and it's gonna fail. So we can just do that. And oh, in this case, it actually failed after the 4th time. Let's do it again. Ooh, that time it lasted 105 times. So fortunately, I didn't break the Discman. It was probably one of these ones that lasted a bit longer. 83, 44, pretty random. Oh, this is pretty random. Yep, super random. Okay, cool. So, oh, look at that, 3 times. Wow, fail. I'm gonna put that one on fail block. Okay, so you can do failure. Now, let's say you want to do some kind of a distribution. You know that lots of things are normally distributed in the world. Lots of your data is probably normally distributed or not, much to your chagrin if you're trying to use some test that requires it. And you can use this thing called the Box-Mueller algorithm to take a uniform random number and actually get out a normally distributed random number. So we can do that, hopefully. Yep, there it is, cool. So that looks like it might have come from uniform random. There we go, there's a -1. So this is a normally distributed number centered at 0. So we can really build any kind of sample we want, all from a uniform distribution. But of course, we're not going to do that, right? That would just be crazy because Python and really any tool you have has built-in algorithms that are much faster than the Box-Mueller algorithm, for instance, for generating random variables from a distribution of your choice. So here you can just use random normal. That's going to give me a single number from the normal distribution. You can do that over and over again. Random. Then you can actually look, numpy.random has lots of different distributions. All your favorite probability distributions are in there, the beta distribution, binomial, et cetera, et cetera. And we can get a whole bunch of them and actually plot a distribution of all the data points we took. So, you might have been slaving away at some project, collecting a bunch of data, and then you realize, oh, I could have just made it up. Because, here's heights of humans. I went out, I could tell my, boss that I measured thousands of humans and here's their distribution of heights, or I could save myself the time and, generate randomly. Okay, this is all just to give you an idea of what you can do. Not that you would do that, not that you're that disingenuous, but just to give you a bit of a primer, these are random numbers. So a little side note before we move on, we're of course talking about pseudo-random numbers. So one of those guys, the horseman, Feynman, it was von Neumann had a quote about something about the folly of trying to use a deterministic machine to create, randomness. And, of course, that is folly. And so these numbers aren't truly random. If we know the starting point, we can reproduce exactly some string or sequence of random numbers. So we can set a seed, and we'll get the exact same random numbers back again. So if I set that seed and draw this distribution, you can see there's a little bump there. I'm going to set the seed again and draw the distribution again. I got the exact same set of numbers. Okay, so they're random within, given a seed, they behave as random, but they're not truly random. And that can actually be really useful to use that property to have reproducible results when we're using Monte Carlo methods. Okay, so you can do beta distribution here. Beta is one of my favorite distributions, ranges between 0 and 1, often used to represent uncertainty in your estimate of a probability, which is cool. Gumbel distribution, also super cool. That's known as the extreme value distribution of maximum points in a normal distribution. Poisson is also pretty cool. You've probably seen that. Generates integers, counts. Okay, so that's just an introduction to RUnif and then the spin-offs and all the things you can get from a uniform random. So drawing samples is cool, but we want to actually do something with these, free or seemingly free. We can generate thousands of them, hundreds of thousands of them very fast, and we want to do cool things with them, right? So what are some of the cool things you can do with random numbers? So one of the main things I like to do with them is to understand statistics better. So understand where, potentially obscure statistics come from. How do they work? What's up with that? Why do we use a chi-squared test? Why do we use a t-distribution? What are those? Some people did a lot of math back in the day, figure out that those distributions are appropriate, but we just sort of take their word for it. So I like to use random numbers and Monte Carlo to sort of confirm that things actually behave the way that the stats textbooks tell us they do. So for this, I just want to give a little demo. So this one comes from actually a biostats course I used to teach where we were talking about Mendelian genetics. And if any of you took genetics, you might remember dominance recessive relationships. And the dominance recessive relationship in genetics predicts a 3-to-1 ratio of phenotypes, of the dominant to recessive phenotype. And in this case, we might be talking about butterflies, and the dominant is yellow and the recessive is silver. Okay, and we teach the students that you go out there and you count and you test whether this is truly a Mendelian ratio happening in your data set, and we tell them use a chi-squared test, and they just sort of take your word for it and dutifully record the chi-squared value. And I find this very helpful to think about why that works. Okay. So what we're going to do here is we're going to go out and pretend we went out in the field, we got our nets, and we captured 20 butterflies, and we recorded them. We did a chi-squared test. But since this is Monte Carlo and it's in the computer, we can actually do that same field experiment hundreds or thousands of times, okay, and actually see what the distribution of our test statistic would have looked like if under the null hypothesis that the Mendelian ratio is true. Cool with that so far? Good. Okay, so here's the very first one that we drew. 19 yellow, 1 silver. Down on the bottom, I'm plotting the experiment number there. So it's experiment 1. And on the y-axis is the chi-squared value that we calculate. So, you can look it up in Wikipedia, observed minus expected over something. Someone, I don't know. You can look it up. Observed and expected are in there somewhere, but it's a calculation based on what you observe. Compared to this ratio that you would expect, 15 and 5, right, would be the expectation of a 3-to-1 ratio for n of 20. And you calculate this value, and here you get 4.267. And actually, in this case, we've exceeded threshold for statistical significance, right? Everyone wants statistical significance. It's great. And so you go and you could publish this and say, these butterflies are not following a Mendelian ratio, and somebody needs to go back and do the genetics. I But so you can imagine doing this, multiple times and seeing what happens. So on the top, I'm just going to plot a histogram of what happens if we went back and did this experiment over and over again. So let's do it a second time. This time, 3 silver, 17 yellow. We're down there at a chi-squared of 1.067, and our distribution is starting to build. We got 2 bars. Go out and do another experiment, this time 6 and 14. So you can see that's very close to the expectation. So the chi-squared is very small, and we would have not rejected the null hypothesis. We would have said, yeah, seems legit, is totally in line with Mendelian ratio. We have no reason, no evidence to suggest that we should reject that hypothesis. And we, in this case, go, I'm not going to publish today, who earns, and we move on. But we send our undergrads out into the field and get them to collect more butterflies, and we keep going. And so we can imagine doing this experiment over and over and over again. Let's just a whole bunch of times. And you can see that the test statistic that we collect every time we do it is starting to form a distribution up on the top right that is looking pretty good, cruising along. And then I just, at the very end, let's just plot on top of that what the chi-squared distribution is for the appropriate number of degrees of freedom. And, presto, it fits on top of the observed chi-squared distribution, under the null hypothesis. So I find this kind of thing really cool. It's really helpful to think about where these distributions come from. There's also a very cool implication here, which is that in this scenario, we were omnipotent, right? We set up a world where we were generating samples from a real population that had a 3-to-1 ratio. So I randomly generated silver and yellow from an underlying distribution that actually was exactly 3-to-1. So we knew exactly what the population was, and we were able to see that under that population assumption, the distribution works out as we expect. Okay, so so that's cool. Understanding statistics. Oh, let's look at another example. Let's look at this one. Okay, so you may have done linear regression before, and you may have seen that. Okay, I can get a t statistic out of that, and I can get this f score or this f ratio, and you're like, oh, I don't know, what's the p-value? I don't know how to interpret those. So we can do the same kind of experiment that we did with the in silico butterflies, and we can set up a world where we know what the true underlying regression line is, what the true relationship between independent and dependent variable is, and we can draw some samples from that regression, right? So this is just drawing random numbers using Monte Carlo, and we can calculate what our slope estimates are, our intercept estimates are, and we can also calculate the F ratio. And we can start to look at, if we do the same thing where we just run this experiment of observing data from this true underlying distribution shown in the dotted line, we can see how our estimates vary and what kind of distributions they follow. And so in this case, the underlying relationship is a slope of 1, so the F distribution doesn't follow the null. It would follow the null if there was 0 slope, right? If there was no real relationship between the independent and dependent variable. But you can also see, interestingly, that your slope intercept, so your slope estimates and your intercept estimates are t-distributed as expected, and they have the variance that is expected from the tests. So there's lots of very elegant math that goes into knowing that that's the distribution, the F distribution, that it follows that. And back before there was Monte Carlo, there were people doing this math and writing the equations for these distributions. But now that we have Monte Carlo, we can actually empirically determine what these distributions are because we can just repeatedly run these experiments. So it's cool because it helps you understand, but it also gives you another superpower, which is to create your own statistic. Okay, so a statistic is really just anything you can calculate from an observed quantity that you know what the distribution is under some assumption about the underlying process. Okay, so that sounds maybe a little bit abstract, but And I'm realizing, unfortunately, my example isn't going to be any less abstract or hard to understand, but this is an example of creating your own statistic. This is actually one I did in previous life, where we were looking at identifying significant deviations between model predictions and observed data. And the way that we created this statistic, which didn't exist before, which isn't in the statistics textbooks, is by using Monte Carlo, by using randomization to understand the properties of this statistic and to evaluate that it had the appropriate characteristics, that you would have type 1 error rates that were as expected, 0.05. But that's kind of a complex example. But it's really anything, any system that you have that you can generate data from, that you can simulate data from, you can generate your distribution under your null hypothesis, or if you go in for that kind of thing, which I'm sure Austin doesn't, being Bayesian. But once you have that distribution, then beyond what threshold would I need to observe in this statistic in order to reject the hypothesis that this null world is the true world that generated the data. Okay, so that's cool. You can understand statistics. You can make your own statistic. You can also avoid having to do some hard math, and in some cases, impossible math. So kind of the canonical example of hard-ish, but not impossible, is, let's see if I can find it. Oops. Okay, I'm going to skip that example. I was going to show the canonical example of estimating pi. I lost my PDF for that. Okay, so you can estimate pi. Go look it up. It's pretty cool, but you can also do some other hard, that's like hard math, but not impossible, because like you calculate pi using better means. But we can do, as Ullman and Feynman and von Neumann were thinking about, we can do impossible math, and we can do some integrals that we wouldn't be able to do in closed form. And we can use this trick that you've probably heard of called Markov chain Monte Carlo. And that's a flavor of Monte Carlo where you follow this guy's rules. And his sort of life philosophy was, where I decide to go next depends not on where I've been or where I may go in the future, but only where I am right now. So if that's your life philosophy, best of luck to you. But this works out nicely mathematically and allows you to actually explore unknown distributions in a way that allows you to effectively integrate them. So there's a specific kind of the Markov chain Monte Carlo called the Metropolis-Hastings algorithm, and I think of this as being a little Markovian explorer that goes out there and picks some random starting point in the distribution or on the surface that you're trying to explore, chooses a new location within the vicinity, and then goes to that location according to some probability. It's just the ratio of what the surface, the height, sort of the value of the function at that point versus the value of the function at the new point, and then otherwise stay where you are and then repeat. And so if we can do this over and over again, and you can see at the heart of this is just generating random numbers, right? Generating some new location to go to, and typically you do that from like a normal or a Gaussian distribution. So we can see this in action. Hopefully I didn't lose this one. There it is. Okay. Okay, so here's Dora, the Markovian explorer. The target distribution that we're trying to integrate under, I'm showing on the top there is the blue dotted line. Also shows up at the bottom. The choose a location in the vicinity is this more spiky normal distribution there, and the current location is shown as a green dot. And then we're just we're gonna show where we've been in this middle panel in the trace. And so we can do this, follow this simple algorithm, choosing a location, deciding to go there based on the ratio of the function value at that location to the function value where you were, and not otherwise. And we can start wandering around this distribution, recording our location, okay? We're recording where we've been. And it turns out that there's something called an ergodic property of this algorithm, which actually guarantees that under enough samples, you will actually converge to having explored the distribution in proportion to the distribution itself, which is like another way of saying, in the end, you'll have a bunch of random samples from this unknown distribution, which is really pretty awesome and super powerful. Austin's going to talk more about it. Here it is in action. This is pretty cool. Oh, another thing that just happened there is this was a modified version of the Metropolis Hastings algorithm where it was adaptive. The proposal distribution or the distribution deciding where to look was adapting as it went along to try to be more optimal to explore the space better. Just a little trick. So you can see how the trace went from being very autocorrelated early on, and then it sort of spanned out to sort of capture the whole region of the distribution. Okay, so that's a cool application, pretty random. You can also use random numbers to understand what inferences you can make about your data, okay? So you have some data, and you have some idea of like a model that generated that data. So you have some conception of the world, you have some theory, you think you understand what's going on, you don't, but you think you do. And you proceed on. And so you can actually use randomization to get a sense of whether you can make the kinds of inferences from your data that you want to make under the assumption that the world works as you think it works. So here's a cool example of that. So this is from a really old Kaggle competition that I did that was on detecting dark matter using pictures of the sky where you had background galaxies represented as just elliptical slashes across the sky, effectively. And the idea was that under the assumption that there's no dark matter between you and those galaxies, their configuration in space would be random, right? So we have no reason to believe there's any structure in the universe that would make the configuration of galaxies that we look at in the night sky anything other than random, which is nice. Okay, cool. There's randomness there. And the only thing that would deviate these galaxies from randomness is the presence of something very heavy between you and the galaxy that actually warps space-time itself in a phenomenon called gravitational lensing, which is very cool. And the challenge was, okay, you only can see the galaxies, and now tell me where the dark matter is. Okay, so. Pretty neat problem. Doesn't fit into like, classification or regression. It's kind of a pretty custom problem. So we start with trying to understand, here it is. Start by trying to understand how would the data react in a world where you were controlling what was going on. So to work on this problem, what I did was I looked into what are the dominant models of gravitational lensing, like what's the functional form of how lensing affects the ellipticity of nearby galaxies. And I found this form, I forget what it's called. There's a few competing models, but here's one of them shown on the right. And what it does is that little sort of hockey shape close to the origin is showing that close to the dark matter, the ellipticity is being skewed more heavily, and that's decreasing as you go further away. And so instead of using just like applying this model to the data and hoping for the best, the idea here was to say, okay, if this was the true model, could I detect the dark matter halos and the lenses given the data that I have available? And the best way to do that is to use that trick I talked about before, which is to be omnipotent, right? You can generate a world where you know exactly what's going on because you built it, right? And it's a really amazing tool to be able to try to tackle problems and really get a deep understanding of what's going on, and then evaluate whether your inference algorithm will actually be effective. So in this one here, I'm just showing you can take this model and then increase the size, the mass of that dark matter halo in the middle, and you can see how it actually will start to lens these surrounding galaxies, right? And so you can see it's contorting the apparent ellipticity of those galaxies in the background as a result of its weight. And so this was just to show that, okay, under this model, this is how this would have this effect. And so we understand the relationship between the ellipticities and distance from the halo. And so effectively, you can now fit a statistical model to that curve and try to find in the frame where the dark matter is. Okay, so using random numbers to understand a system and understand what inferences or whether you can distinguish your model from a competing model in that environment. Also use this technique to understand how multiple halos would interact in the same frame. Because as you saw in the example sky that I showed you, there were 3 different dark matter masses, and they were all having simultaneous impacts on the distribution of the background galaxies. So this little simulation is just showing, how does the ellipticity of all the galaxies change as you have kind of interacting halos? And can we, from this data, still infer the shape of that distribution? So I'm just showing one visualization of a single instance, but the idea was I use this process to generate multiple skies and fit the model to see how well is it going to fit what I know is the reality of this case. Okay, what I know is the distribution of the lens itself and the location of the dark matter. So that was kind of a cool use. Okay, so you can do that. Number 4, you can use Monte Carlo to propagate uncertainty in complex predictive models. So randomness can be thought of as like stochastic events, like things like throwing a dice, but it can also be thought of as like things you just don't know, right? So your state of knowledge in the world can be represented as a probability distribution. And as Austin squirms, wondering whether I'm going to, steal his talk, I'm not. See next talk for more information about that, but super cool use of Monte Carlo methods there. Finally, there's lots of other things, but I just picked 4 to not bore you too much. Finally, number 4, you can run what-if scenarios using Monte Carlo. And by that, I mean you can create a generative model of the world of data, and then you can tweak aspects of that model. You can tweak things that are going on in your simulated world and ask what would happen under these scenarios if I made these changes. And so to make that a bit more concrete and to give an example from my current role at Penn Medicine, this was a little experiment that I was doing with understanding how patients move from one unit to another in the hospital system. And so I trained, again, a Markov model, not Markov chain Monte Carlo, but Markovian in the sense that patients move to a new unit based on the unit that they're in now with some probability. So I fit that probability matrix with data, with looking at all these patients in the hospital system. Where do they go? They enter through the ED, then something else happens. And then we can start asking like lots of questions about what would happen under different scenarios now that we know kind of how patients move through the health system. So you might ask a question like, where would we expect to see a surge in patients? Sorry, if we were to see a surge in patients in a given unit, what knock-on effects would that have throughout the rest of the health system? You can use this kind of approach to just run that over and over and over again and see that happen. That same weird day where that surge happened, you can run that thousands of times and say, this is the distribution of outcomes that happens in the event that you get this surge in this one unit. Yeah, so I had a bit of code to show for that, but I won't bother. So I'll just sort of finish with a word I made up, because why not? That's pretty random. Start on a random note, end on a random note. Simudidactic, okay? This is from the Latin root, simular, or from similis, and the Greek root, because Greek and Latin, just put them together, why not? Dictatos, for taught. Okay, and I think of this as sort of the process that one does when they have this great power of random uniform numbers. and computers, that we can use those to understand the world by creating a representation of the world, a representation of phenomenon in the world, and then using these techniques of randomization to understand complex processes. So feel free to use it in a sentence whenever you want. It's fine. Creative Commons license, you know, you don't have to, whatever. So yeah, so it's the idea of, you know, just thinking about randomness and using, and then, you know, if you have an idea of, oh, what would happen if, you know, in this scenario, go to your computer, you can simulate it. It's very easy. We have all the tools. Okay, so that's intro to Monte Carlo. Can't leave without the pitch. If you're interested in Monte Carlo or any other machine learning topics, including machine learning, but you are a software engineer, either senior or mid-level, and you want to come help us out building real-time predictive applications and our core platform, Penn Signals, check us out at that URL. Talk to me, talk to Mike Becker, who I'm sure you guys all know, and that would be great. Love to have you come work with us. Any questions? Yeah. Yeah. That's correct. Yeah. So the question is, can you use the observed data of where patients go in the hospital to invert the problem to just like look at what are the dynamics? And in fact, yes, that's exactly what was done there. And that the graph I showed was just under the normals, under status quo, right? So it was fairly simple. You just count up the number of times you see patients moving from one unit to the other, make that a cell in a matrix. Just count those all up, then you normalize all the rows to, you know, so they sum to 1. Then you have these transition probabilities of, given that I'm in the ED, what's the probability I'm going to go to a perioperative unit, right? Compared to what's the probability that I'm going to go to an ICU. And then you can just draw a random patient from that. In fact, I will go and show this real quick. Patient flow. So you know, just taking some data of where patients went. You create this, they call it an adjacency matrix. That's this, you know, unit to unit probability. And then once you have that adjacency matrix, you can do cool things like just, you know, making a fake patient that never really existed, but behaves statistically like other patients it's seen. So this patient came into the emergency department 420 minutes into their stay. They went to Cathcart 7, which I don't know what they do at Cathcart 7, something. Give Band-Aids or something. Well, maybe not, they don't do a very good job because then they go to the intensive care unit. Things got worse. Then they went to this, you know, whatever. So this isn't a real patient, obviously. I'm sorry, apologize for being glib. But, you know, then they go to this Silverstein 9, which is, I know about that one. That's a floor unit. So they've come out of intensive care and then they're discharged. So this is not a real stay, but one that's statistically representative of a real stay. And this is just one case. And what you can do is generate thousands of them and push them through the health system and see how that changes the census in the different units under different scenarios. You can start pushing them in faster. You could push in a certain kind of patient faster. You could take a unit away and say, this unit no longer exists. They have to, you know, disperse to other places. So you can run a lot of scenarios to discover what would happen. pssimflow.simzomb is there. It's just a stub. Pass. Actually, no, it throws a. Yeah, crashes your computer, something like that. Yes. So, good question. Other questions? Sure. That's right. Mm-hmm. How big of a change does changing a bed? Yeah. To be honest, I didn't do much more than just set up this framework, so I don't know the answer to that. Didn't experiment with a lot of like scenarios and do a very robust analysis. This was just kind of like a proof of concept that like we could use this tool to answer those kinds of questions. Don't know whether it's a massive impact or not. There are also obviously like all models. I showed this slide in my previous talk, showing George Box looking adorable and saying his best quote ever, which is all models are wrong, but some are useful, right? So this is obviously making assumptions about patients and how they move through the system. I assume that they're Markovian in their transit through the system. So once this patient got to the operating room, the model has no memory that they came in through the ED. Whereas you might imagine that that would matter for a real patient. That may change their trajectory through the health system. So of course there's modeling assumptions here. And so, you could do these scenarios, but of course you have to acknowledge that you've made modeling assumptions along the way and that any, inference you draw from it is subject to those assumptions. Yeah, no, it's very, very simple model. You could start layering in those more complex. Yeah. Their next unit would be affected by that, but subsequent units would not because there'd be no memory of that in the model. But the way this works is, so it starts at 0 generic units into the state because every patient comes in to the adjacency matrix from a special row, which represents out of the hospital in the world, right? So it starts with most patients enter the hospital into the ED. So if I simulated another patient, it's very likely they're also going to start at the ED. Yeah. Oh, I see, because it just says emergency department. Actually, we have many emergency departments, that kind of thing. Yeah. Yeah, this is just for one hospital, like one building that has one ED. I believe either that or it's just like the string representation of the department is not showing its full location. It's not showing that this is at HUP versus this is at Pensie's Ravden emergency department, if that's even a thing. Yeah. Oh yeah, that's a great question. And so, so the question was why use Monte Carlo rather than if you have a Markov model? I'm presuming you're getting at because you can just use like there's steady state dynamics of a Markov model, right? Yeah. So you could do that, and you could sort of understand what is the steady state of by just multiplying the matrix by itself over and over again, or however you do that. It's probably a more elegant way of doing that. And that would sort of tell you like what is the average load in a unit, but you couldn't do like time varying dynamics or like any sort of more complicated, interesting stuff you wanted to do. You go to Monte Carlo, and in fact. Yeah. And it sort of gets at like the thing that really got me into Monte Carlo in the first place was always I would create models and like think about problems and be like, it works like this, and I could write down the model, but I could almost never write down the solution to the model because they'd be like complicated and they have weird terms, and like this weird thing happens like that maybe is time dependent, and I would never have a closed form solution, and so I would just be like, okay, I can simulate stuff through that, and I don't care about the closed form solution. So a lot of like Monte Carlo gets you out of, I think it was my item number 3, like gets you out of doing hard math. And this is a good case. You can make things as complicated as you want and still just push data. I've probably taken sufficient time. So I will turn it over to the next speaker. Austin, thanks.
Thanks, Corey, for that excellent talk. I got to say, this is the second time I've spoken after Corey at one of these DataPhilly events, and it's always a pleasure. He always does a really, really great job. So my talk is really building on his quite naturally. Mine's an introduction to probabilistic programming, and kind of under the covers here, and I'll point out where a lot of that Markov chain Monte Carlo methods that Corey talked about are happening. But the point of my talk is you often don't have to be an expert in those to use them with kind of modern programming packages. And for those of you that know me, you know I'm a big IPython Jupyter person. So I just tweeted the slides for this talk, if you go on my Twitter, if you're interested in this thing. And it's actually generated from an IPython notebook, unlike Corey, who's quite brave running an IPython notebook in real time in front of an audience. I am not that brave. So I ran this before, and then I used this, NB convert to generate a reveal slideshow from it. And that's on GitHub. There's a link to that in the slides itself. So if you're interested in these later, you can just go take a look. Great. So what is probabilistic programming? Well, you think you have some programming paradigms, right? You have imperative, you have functional, you have stack programming, you have a bunch of other junk that I've forgotten since college. What's probabilistic programming? Probabilistic programming is really a programming paradigm where you introduce random variables as a first class part of the language or package, right? Maybe you have a probabilistic programming package inside Python is what I'm going to talk about today, but there are also languages that are entirely built around probabilistic programming. So what's really neat here is that the user specifies a generative model for the observed data, right? And so if you've been following OpenAI recently, they've been talking a lot about deep and adversarial generative models to do things like generate realistic looking pictures. That's cool and stuff, and deep learning's neat. To be honest, I know almost nothing about it. People have been using generative models for forever in non-deep context. So it's really powerful because the way I think of a generative model is it kind of allows you to tell the story of how your data was generated. So basically what a probabilistic programming language is going to allow you to do is write a program that describes how your data was generated, feed it in observed data, and then it's going to perform inference for all the unobserved quantities there. So it's actually pretty neat and quite intuitive, and it can kind of unlock a lot of complicated models that you're like, well, shit. All right, I don't feel like writing an optimization function for this myself. This is going to be a real pain. Like Corey said, you can get around doing hard math that you don't want to do, right? Either that you don't know how to do, or I'm a grumpy old pure mathematician at heart. I know how to do a lot of math. I don't want to do a lot of the math I know how to do. So even if you know how to do it, it lets you get around that. So you tell the story, give the observed data, and then the language runtime or software library, let me make sure this doesn't go to sleep on me, performs the inference for you using a lot of the ideas Corey just talked about. So this is kind of one way to think about this in this pretty sweet flowchart I made this morning. You program a generative model for your data, you collect data, you feed them both into this probabilistic programming language package, whatever. It performs inference and gives you results. And that probabilistic programming can be kind of a black box. People have kind of figured out how to kind of automate some of the things Corey talked about enough to make it so you don't often have to worry about it for a lot of common models. Okay, so what do we mean by inference, right? Well, there's lots of kinds of inference. So let's decide what we mean by inference before we go any further. So here are kind of the three, main ways I think about inference. We can be, just maximize likelihood. We can be a little Bayesian, put some priors on, do maximum a posteriori, which I always have a very hard time pronouncing if I'm not reading it, inference. And while Corey is right, I am kind of a grumpy Bayesian at heart also. Right, there's really a lot of connections. Maximum a posteriori inference is really just equivalent to regularized maximum likelihood inference in a lot of cases, right? So if you believe in regularization, you're more Bayesian than you think you are, right? And all good data scientists believe in regularization. Here we're going to work for full posterior inference. right? So that's what Corey said. We're going to actually try to use those. He gave an example of the Metropolis Hastings algorithm. That's going to be one in our stable. There's kind of an infinite variety of things. There's Gibbs samplers. There's Hamiltonian Monte Carlo. We'll touch on a little bit. That allow us to sample from distributions that we can't calculate explicitly, like his example gave. And that's what we're going to focus on here. And this is just a favorite little picture of mine that I put in every talk. I believe that's in some statistics department in the UK. I want one. All right. So basically, right now, what I'm going to do is just walk you through a couple examples, I think 4 or 5, of probabilistic programming in Python with a package called PyMC3. To kind of give you a flavor of what you can do. And it's not exhaustive either, in theory or application, obviously. And we're going to work from really simple examples where we can work out the math really easily. As a matter of fact, I'll write the math on these slides, right? Because if we can't, replicate things we can do by hand, we don't really know what we're doing. We shouldn't trust it when we can't do things by hand. So we're going to start from some simple problems we can definitely work out with pen and paper and work up to some more complicated, some things that are pretty close to the state of the art. One of my favorite models in political science for measuring, the partisanness of Supreme Court justices or something like that. It will be our final example. All right. So I'm also a former teacher. This is a question I used to give my It's a Mathematical World students. So if a rare disease affects 1 in 10,000 people, and the test for the disease gives the correct answer 99.9% of the time, well, what's the probability that you have the disease if you test positive? We'll see the answer in a minute. It's definitely not 99.9%, as hopefully we all agree, but we'll get there. So let's start with a simpler question. What's the probability that if I take someone off the street, don't know whether they have the disease or not, that they test positive? Okay, here's kind of our introduction to PyMC3. So here we're going to tell a story of how our data was generated. And let's see, I should have tested if this is a laser pointer, and it is. Right, so we build a model, and first we decide, does the person have the disease or not? Okay, well that's like a coin flip, and the probability that they do have the disease is 1 in 10,000, right? Does that make sense? So that's, Bernoulli is like flipping a coin, and the probability that that coin comes up positive for the disease is 1 in 10,000. Okay, now given whether they have the disease or not, we can know the probability that they test positive, right? So bear with me with this T dot in a second. I'll explain why that's necessary later. So this is just like an if statement. T dot switch. If this evaluates to true, then it gives you the first. If not, it gives you the second, right? Okay. So if has disease is equal to 1, they have the disease. They test positive 99.9% of the time. Cool. If it's not 1, if it's 0, they test positive 1 minus 99.9% of the time, right? Okay, so this tells me if I know they have the disease, I'm telling the story of my test results here. I know whether or not they have the disease based on this coin flip. This tells me the probability that they test positive or negative given whether or not they have the disease. And then we flip another coin to determine the outcome of the test based on this, either this 99.99 or 0.001, right? Okay, that's not too bad. So I forgot this doesn't work with these presentations. Great. So I'm not going to talk a lot about what goes on under the covers here, but what we basically are doing here is sampling from that distribution using the methods Corey talked about. But notice that you don't really need to know anything about that here. You could have even actually left out selecting the Metropolis step here, and PyMC3 would have automatically selected a good one for you. It's just kind of a force of habit for me to select the one I want. I probably should have left that out for the purposes of this talk. Great, so we draw 40,000 samples from this. And, in this trace, we get 40,000 values of whether or not they tested positive, right? And most of them are 0, but as we'll see in a second, some of them are 1. Okay? So let's see. If we take the mean of that, which is really, add up all the ones, divide by the shape, divide by the size, the mean is just a shorthand way, that tells us about, 0.15% of people are going to test positive for the disease. That makes sense. It's pretty rare, and false positives are pretty rare. Okay, and hey, we also know the law of total probability, so we can calculate this by hand. And that's about, 0.11%. So we're not too far off. That's an okay estimate, especially, if you think about orders of magnitude. If you wanted a more accurate estimate, sample some more. Throw some more computer time at it. Okay, now that's fine. That's not that interesting. Let's talk about, what happens when we have observational data. What can we infer about some hidden factors, right? So if someone tests positive, what's the probability that they do have the disease? Okay, now this model is quite similar. It's actually almost identical, except you'll notice down here I put observed equals 1 for test positive. This is saying, hey, the story of how this data was generated was still the same, but I've observed that they've had a positive test, okay? And then I'm going to run, samples from this. If this will stop pinwheeling. And then, hey, we can go back and look at how often do they have the disease, given that the observed test was 1. And that is about 9.7% of the time they have the disease, okay? And once again, knowing Bayes' theorem, we can calculate this explicitly. And the correct answer is about 9.1. So once again, we're off, sample more to get a more accurate answer. But we're order of magnitude correct, right? We've disproved that the answer is 99.9% likely, right? So this is kind of the simplest example you can give for this sort of thing. It's good to do one example you can work out by hand. I'm actually going to give 2 examples you can work out by hand because I love the Monte Hall problem. It's a great problem, right? So, what was the show called? Let's Make a Deal, something like that. The host's name was Monte Hall. And, the contestant would be presented with 3 doors, right? Behind 2 of the doors is a goat, and behind the 3rd door, I don't know, is a nice car or something like that. The contestant would choose one of the doors first, right? And so Monte would open one of the other 2 doors. He knows where the actual prize is to reveal a goat. Right? And then he would ask, do you want to switch or stay with your door? And then, after you decide to switch or stay, we're going to open it. Right? And so this is kind of one of those classic probability paradoxes everyone's read about on the internet. The answer is you should switch, right? You can work out, again, using like 2 layers of Bayes' theorem that you should switch. Let's see how to do that using PyMC3. Okay, so we choose the first door, and Monte opens the second, or the third, sorry, to reveal a goat. What should we do? Well, kind of dutifully, we're going to build a model, for a generative model for this problem, right? So initially, we have no idea where the prize is. So we just believe there's a 1/3 chance it's behind door 0, 1/3 chance it's behind door 1, 1/3 chance it's behind door 2. That's what this part's saying. And then, again, bear with me, this t.switch, t.equal will make much more sense later. When we talk about some of the more advanced things we can do, because PyMC3 is built on top of Theano, if you've heard of that. So now, just like once we knew someone had the disease, we wanted to determine the probability that they test positive. Okay, if we have a sample from where the prize is, we want to determine the probability that Monte opens each of the doors, right? Okay, well, first, I think it's pretty obvious that he's never going to open the door we chose, right? That's pretty clear. Because then we obviously will either, the stay or switch decision is made for us. There's no drama for the television, right? So in each of these cases, he's never going to open door 0 because we've selected that. So if the prize is behind door 0, which is the one we picked, he can choose to open either of the other doors, right? And we have no reason to believe he favors one door over another. So we say, okay, he's not going to open the door 0, and there's a 50% chance he's going to open the other 2, right? Okay, and if it's not behind door 0, if it's behind door 1, well, he's not going to open door 0 because that's the one we chose, right? He's not going to open door 1 because then we would know which door to switch to. That's kind of stupid too. That doesn't preserve the drama for the television. So he has to open door 2, right? So that's this. Definitely not going to open either of the first 2. Definitely going to open the last one. And then in the case where it's definitely behind the 3rd door, he's forced to open the 2nd, right? This makes sense, kind of intuitively. And then we see he opened door 2. We've observed that he's opened door 2, okay? So, we do the thing we've been doing for a while. We sample from this distribution. In this case, we transform it to a data frame. And here we have, 10,000 samples from where we think the prize is. So in sample 0, the prize was behind door 1. In sample 1, it was behind door 0. In 2 through 4, it was behind door 1, right? And what we can do is look at how often was it behind door 1 versus how often was it behind door 0. That's the probability of where it is based on what we've observed from him. So, we do that. Pandas is great for this sort of thing. If you haven't read those blog posts by Tom Alpsberger recently on modern pandas, they're fantastic. I never knew you could chain methods like this, and it's just beautiful. And so we do this. We group by the prize. We see how often the prize is behind door 0 versus door 1. And we see, if you do this analytically using a couple layers of Bayes' theorem, you see the actual answer is there's a 1/3 chance it's behind door 0 and a 2/3 chance it's behind door 1. So you should switch. And these, once again, are not that far off. If you want closer, sample more. That's fine. So here are the two we can work out by hand. We're going to kind of leave behind examples we can work out by hand now, but it's kind of good to crawl before we walk, before we run, I think. So let's talk a little bit about PyMC3 now. This is just kind of a description from their website. It's a Python module forbidding Bayesian statistical modeling and Monte Carlo fitting, which focuses on advanced Markov chain Monte Carlo fitting algorithms. Its flexibility and extensibility make it applicable to a large suite of problems. How many of you have used PyMC3 before or heard of it? Very cool. Not all of you are my coworkers who I've probably forced into using it, so that's pretty neat. I love PyMC3. I'm a contributor. It's a great project. You should contribute to it if you can. It could use a little help getting out of beta. It's kind of a labor of love by a smallish group of people. And it's built on top of Theano. This is where this capital T came in. Now, how many of you have heard of Theano before? Right, most of you. That's awesome. So Theano is used a lot for deep learning, right? It's used to build kind of these symbolic pipelines. It's a competitor for now TensorFlow, right, which has backing from Google. And it allows you to do some really cool things like build up those DAGs of computations. But what's also really great for is automatic differentiation. Right? It will automatically compute gradients, Hessians for you, stuff like that. And so that allows us to use some advanced Markov chain Monte Carlo techniques that rely on gradients and Hessians, this Hamiltonian Monte Carlo I'm talking about, right? And so just like we often, if we can reasonably compute a Hessian, prefer the Newton-Raphson method to gradient descent because we take into account the curvature of the space we're optimizing through, right? Obviously modulo a bunch of other practical concerns like can I compute the Hessian in memory? We tend to prefer Hamiltonian Monte Carlo to regular Monte Carlo when we can because it takes into account the curvature of the distribution you're trying to approximate to do it more accurately and is related to, I don't know exactly what sort of adaptive Monte Carlo Corey was doing, but the ideas are certainly similar. You should adapt to the curvature of the distribution. So this is one way to do it. It has some other nice features. It automatically generates C code. But to get that automatic differentiation, you have to do things like not using Python's if statement, but that t.switch. So Theano knows how to differentiate the result of an if statement. That's basically the reason you need to do that somewhat contorted syntax, but after you get used to it a little bit, it's not so bad. It implements the no U-turn sampler, which is kind of a fancy Hamiltonian Monte Carlo. Another problem with these things, and like I said, I'm not going too in-depth on these, is that they come with a lot of parameters you have to tweak in order to get good behavior on them, kind of regular Hamiltonian Monte Carlo, things like that. The no U-turn sampler is a great one in that it does some reasonable auto-tuning on its own. So that's pretty cool. Okay, now on to example 3. This one is close to our heart in Monetate. It's A/B testing a website. Right, so what's the idea in A/B testing? Someone thinks a blue button is going to get you to buy, more people to buy. Someone thinks an orange one's going to get more people to buy. So we serve each to 50% of the traffic, and we try to decide in the end. Now, working at Monetate, I have to tell you, it's not 2001 anymore. This isn't actually going to make you money, but you need to test harder things, more difficult things. But this is the general idea. So, suppose variant A sees, 510 visitors and has 40 purchases, and variant B sees 505 visitors and has 50 purchases. Okay, and what do we want to know? We want to know what's the probability that A is better than B or B is better than A? Which one of these is better? Which one of these should we show to everyone, move on, try other things if we want to make more money? Well, we can talk about how the data was generated here in 2 ways. It seems reasonable that, purchases is a binomial distribution, right? There's 510 trials for variant A, and there's 40 observed ones, right? And, what do we want to know about the probability? Well, a priori, we don't know anything about the probability. And you know, if you're a really grumpy Bayesian, you'll say maybe uniform is not the best way to encode that, but whatever, fine. Uniform is fine here. So we use a uniform prior to indicate that we have no idea what the conversion rate is going to be for each variant beforehand, right? To encode that we have no idea there. Corey talked about the beta distribution. This is just a special instance of the beta distribution, which is, of course, the conjugate prior for the binomial distribution, right? So we set these two systems up. We have the A rate, we have the B rate. We've observed conversions for A, we've observed conversions for B. We want to know which is better. So we sample. And here I am using that no U-turn sampler. Hamiltonian Monte Carlo methods, because they're, you know, rely on gradient, and Hessian information can only operate with continuous parameters, right? So those ones before where we had discrete parameters don't really work with those methods. You can build hybrid methods, but it's more detail than we want to get in here. Okay, and so we look at the posterior distributions for each purchase rate for variant A and variant B, and we see like, okay, variant B is probably better. It's probably better. Is it definitely better? How much better? Well, you know, we can actually see how often is the sample from A less than the sample from B. That's 72% of the time, so that's pretty good. That can perhaps help you make an informed decision. And what's interesting here is that this is actually a probability, right? If you ask a business person to tell you what a p-value is, they're certainly not going to say, well, it's the probability under the null hypothesis that we observe a value of the test statistic that is at least as extreme. I don't know. I probably just screwed it up. I practiced. So this is nice because this is actually a probability. Now, also like Corey said, this is a probability subject to all of our modeling assumptions, right? And it's maybe more or less sensitive to some of those. George Box also said, one of my favorite quotes of his to go along with Corey's, is that statisticians like artists have the habit of falling in love with their models. So you always need to kind of turn a critical eye there a little bit. But that's another good one from him. He was a witty guy, in addition to looking like the most friendly man ever. So this is cool, and this is, you know, not something we directly do at Monetate, but touches quite closely to a lot of things we do here. Is kind of forms the basis for a lot of the way we think about the world. So one more example that I want to talk about is kind of the flexibility, the interchangeability that this sort of modeling gives you. So let's talk for a second about robust regression. Okay, so here's a data set. This is actually one of Anscombe's quartets, which are, you know, the four famous ones that have the same summary statistics, but like obviously are way different from each other. This is the second or third one, I forget. And so it's pretty obvious that there's one outlier and the rest of these follow a very linear trend, right? So how can we build a probability model to identify this? Well, you know, we all learned at some point that ordinary least squares, because it's minimizing the sum of squares, sum of squared residuals, is sensitive to outliers, right? Because we square that outlier, and well, that's bad. That's bad. So this produces a pretty biased estimate if you believe the line is the true trend, and the other one is maybe just, you know, poorly coded data, something like that, right? There's lots of situations in which you're actually interested in predicting the outlier, in which you might want to do something different. But here, let's make believe that the line is the true trend we're trying to identify. So first, we're going to see how we can replicate this line. I've just fit this with NumPy or SciPy or scikit-learn, I forget what. You can look in the hidden fields of this notebook to see. We're going to see how we can replicate this line with PyMC3, and then we're going to see how we can make one change, one quick change, to produce a much more robust solution to this problem. Okay, so here we're going to build an ordinary least squares model. And to do so, you know, alpha is the slope, alpha is the intercept, beta is the slope here of our line, right? And we're going to put, I don't know, reasonably uninformative priors on those. We have a pretty decent reason to believe neither of them are larger in absolute value than 100, right? And ordinary least squares is equivalent in some sense to assuming that the errors in your regression are normally distributed, are Gaussian distributed. So here we see that our mean function for our normal distribution is just alpha plus beta times x. So alpha, like I said, the intercept, beta the slope. Right? I don't know. I don't feel like getting too fancy here, so we'll just fix the noise standard deviation at 1, and we'll observe y. So let's see. This should produce something similar to the line. So we do some stuff. And hey, what do you know? The red dotted one is the PyMC3 fit. And it's right on. And we've got a 95% credible interval. If you want to be technical, I guess. Great. So now we've repeated that. Let's think. What's one of the properties of the normal distribution? It's kind of thin-tailed compared to some other ones, right? It puts less mass out at the edges, right? If you go two standard deviations out, you're 94.6, 96.7, some junk. You can tell I haven't done my stats homework in a while. What are some fatter-tailed alternatives? Well, a common fatter-tailed alternative to the normal distribution is the t-distribution with low degrees of freedom, right? Because we need to be careful here. As the degrees of freedom of a t-distribution increase, you converge to a normal distribution, and the distinction's pointless. So here we show a t-distribution with 3 degrees of freedom is fatter-tailed, right? It assigns more probability out here than our normal distribution does. So those tails can absorb some of the effect of that outlier. Let's just swap that out. And literally, we'll just change. You know, here we had a normally distributed error before with some parameters. We'll change it to t-distribution, 3 degrees of freedom. Usually we want to keep it like 3 to 5 in order to not be too normal. And the same mean. Cool. Let's sample. And what do you know? So here's our old plot. And notice in our old plot, a lot of the actual points for the trend we're trying to capture are really kind of on the edge of our credible interval. The outlier makes it seem like this point is also kind of incredible, right? Whereas this one, they're all comfortably inside. And while it's slightly biased by the outlier, still, it's not a perfect fit. There's other things we could do, right? What did I say before? Regularize. We could have regularized those coefficients. So instead of putting uniform priors here, we could have put like a normal prior there. And what would that have given us? That would have given us kind of like a robust ridge regression, right? So if you know ridge regression, that's equivalent with the right hyperparameters to a Bayesian model with normally distributed priors on the coefficients. That's another thing I love when there are kind of Bayesian frequentist arguments, right? If you believe in L2 regularization, if you believe in ridge regression, you believe in Bayesian linear models. If you believe in the lasso, if you believe in L1 regularization, you believe in Laplace priors, right? So there's a lot of equivalences here that learning this sort of thing kind of is intellectually stimulating to me also, in addition to being useful for data analysis. So here's my final example. This is one of my favorite models in real life. This is an ideal point model. Right? So how many of you have seen, on 538 or whatever, ratings of like Supreme Court justices by ideology, right? I looked one up today. Supreme Court justices get more liberal over time, and they theorize a bunch of reasons this could happen. This is kind of the core of the method they use to generate those ideological scores for justices. This is kind of like the basis of that method. People also use it for adaptive testing, test scoring, right? You can think about, instead of the ideology of a congressman and the ideology of a bill in front of them, you could think of those things as the difficulty of a question and the intelligence of a student combined to see how likely the student is to get that question right, or the conservativeness of a judge and the conservativeness of the case in front of them combined to tell you how likely they are to vote for or against that motion. Okay, and so here we use some data from the UC Irvine Machine Learning Repository on 1984 congressional votes. And I've slurped this in. You can find the exact URL in the background in this notebook if you download it. Encoded these things. NANs are missing votes. PyMC3 actually has great missing data capabilities to impute what the posterior distribution is there. I just dropped it here for convenience. Didn't want to get that complicated here. And we see I've coded party as 0 for Republican and 1 for Democrat. Okay, so these up here are bills. So the first representative voted against the first, for the second, yada, yada, yada. So here you can see kind of how party voting broke down across bills, right? And one interesting feature here is that you can see some bills are fairly partisan, right? Like Bill 3, very few Democrats voted for, but almost every single Republican voted for. I forget, I looked this up in the coding. This was some aid to military resistance in Central America, something like that. Bill 1 enjoyed moderate bipartisan support, right? About half of each party did. So it's reasonable to believe that each of these bills will have a different ability to tell Republicans from Democrats, right? If we're trying to turn these votes into a score along, say, a conservative liberal spectrum, some of these things, for example, which way you voted on Bill 3, is going to be much more telling than which way you voted on Bill 1. So keep that in mind for a second when we posit this ideal point model. Okay, so Pij here, and this is the most complicated math we do here, so I hope it's not too bad, is the probability that representative I votes for Bill J. And we encode it this way. You know, gamma, alpha, and beta will be useful for the next slide. I'm going to use those in my model. But what that really means is the ability of Bill J to discriminate between conservative and liberal, right? So for Bill 3, that might be high, and for Bill 2, or for Bill 1, that ability to discriminate might be low. Right? And then the conservativity of representative I, you just have to pick a point to label as positive. You could choose liberal. Kind of the political science literature kind of uses conservative as the positive direction as a convention. So I don't know. I don't know who established that. We'll just follow it here. It doesn't matter, right? If you multiply everything by negative signs, if you multiply gamma, alpha, and beta all by -1, you get an equivalent model. So it doesn't matter. Minus the conservativity of Bill J, and you'll see we have the log odds here, right? So this is really saying the probability that they vote, that representative I votes for Bill J, is a logistic regression on this ability to discriminate times the difference between their ideological positions, right? The kind of intuitive idea here is you place these people and bills along a spectrum, and everyone has a bill ideologically that they're 50% likely to vote for, right? If the conservativity of a bill is exactly equal to your conservativity, right? So that difference is 0. There's a 50% chance you're going to vote for that bill and a 50% chance you're not. If you're much more conservative for that bill, you're going to vote for that bill probably, right? So we can begin to see how this works. And so we code this up in PyMC3, and it's not that bad, right? It's not that bad. It really involves 3 groups. Then we force it through a sigmoid function because we're doing logistic regression here. You know, if you notice the difference in complexity for some of these priors, that's good. You have to constrain certain values in order to make this model identifiable. That's kind of the one place this gets a bit technical. Like we force the mean of alpha to be 0 in order to keep this model identifiable. And this is really great because each of these has a shape applied to it. Right? So alpha is the conservativity of each representative, and we have n reps representatives. So this is a vector of normal distributions, each that can move somewhat independently of each other. This is the conservativity of the bill is a vector of normal distributions that share a common prior, right? So this is a hierarchical model. It's a non-nested model. You know, this all kind of goes through the discrimination of each bill to determine whether you vote for the bill or not. Well, and you sample this, yada, yada, yada. What's really cool, it separates Democrats and Republicans. This is just awesome. This is so neat to me. It separates Democrats and Republicans, and you can tell which Democrats are more conservative than some Republicans, and which Republicans are more conservative than some Democrats in this 1984 Congress, based solely on their voting record, no other labels involved. Really neat. You can do this to do things like impute missing votes and see if the absence of people changed whether or not a bill would pass under your model, or the likelihood of that under your model. Now, I did this here, and the results weren't that interesting. The answer was no. So I chose not to show it. And we can see here which bills discriminated better, right? Ones to the right are better at discriminating. Far away from 0 is better at discriminating. The sign just tells you whether more Republicans or more Democrats voted for that bill. So like we said, Bill 3 before, that was 0 index. Sorry, this is 1 index. So Bill 4 here is pretty good at discriminating. Bill 2, not so much. So pretty neat, pretty neat. This is called Myers-Quinn scoring, something like this. So this is scores for each Supreme Court justice over time for the last 60 years. So what's really neat here is that was one term of Congress, right? You could extend this model to time dependence by saying there's some auto-regression, right? In the 1986 session of Congress, my conservativity, if I was reelected, should be allowed to move, but not by too much from my 1984 conservativity. And so you can produce this dynamic ideal point model, which people use to predict Supreme Court cases quite well, I think, to some interesting results. So this is one of my favorite models that finds a lot of application in political science and kind of education technology, all sorts of interesting things. So that's the end of my models. I wanted to talk about kind of the broader probabilistic programming spectrum of tools. I've listed 5 here. There's a lot more, okay? Put PyMC3 at the top because that's the one I like. That's the one I've chosen to, write code for, contribute examples to the online repository. And there's kind of, I've broken them down along kind of 4 things. What languages do they support? Do they support discrete variables? Because Stan, which is another excellent one, chooses not to. We can talk about why in a second. Do they do automatic differentiation and Hamiltonian Monte Carlo? Only 2 of them, PyMC3 and Stan, do, because PyMC3 is built on top of Theano and stuff. And from that comes, and I didn't talk about this at all, but it's kind of an important topic in Bayesian inference, variational inference. The ability to do automatic differentiation gives you the ability to do variational inference. There's been advances in what's called automatic differentiation, variational inference, unsurprisingly. And so that checks those boxes. So PyMC3 is in Python 2 and 3. PyMC2 is in Python 2 and 3. Great little thing, not on top of Theano though, so you don't get any of those kind of automatic differentiation things. Stan is written in C++, but has R and Python interfaces. Does really great work in terms of automatic differentiation. They choose not to support stochastic discrete variables. If you're familiar with the work of Andrew Gelman, he's one of the big maintainers, big proponents of Stan, and I like his viewpoints a lot, but it kills me that he just believes, you just marginalize over those discrete variables and then feed it into Stan. And it's like, well, not everyone wants to do that hard math to marginalize, right? Part of the point of this was avoiding doing hard math, and marginalizing over those discrete stochastics can often be difficult. And then bugs and JAGs have been around for a long time, particularly in biology and ecology. I think bugs, maybe, I forget which. Those are more standalone programs. Some of these ones up here were developed by people who were coming from more of a programming background and wanted the ability to do more manipulation than these, which have been around much longer, were giving them. And they both finally got kind of R ports, I think. So this is kind of a really high overview. I've only scratched the surface of what you can do with these things. There's MIT has a great probabilistic programming researchers group that's built a probabilistic Lisp that they use for all their papers. And it's fascinating, but it's not that useful to applications, I find. I haven't been able to get it to run on my laptop. So here I'm just going to give some references. So like I said, you can find on my Twitter these slides and click these links. PyMC3 example repository has tons of these, that then we could fit in here. 2 of my favorite, because I wrote them, are the survival analysis and the Dirichlet process analysis. But they're all really good, and the Bayesian neural nets one is really fantastic. It's one of the core contributors here. It does way more work on PyMC3 than I do talking about Bayesian deep nets in PyMC3 with automatic variational inference. It's really fascinating stuff to go read that. I would really recommend it. Here's an excellent open source book on probabilistic programming, so what we've talked about today in Bayesian methods. From the perspective of you're a software engineer, go read this. You don't need to know about math. We'll pull the little bit of math you need to know in. This is written in PyMC2. There's a port in progress for PyMC3. That in progress link is to a GitHub branch. If you're interested in this thing, contribute to that. It's fun, but it's also challenging because some of the breaking changes that happened between 2 and 3 made some of the examples not portable. Here's another I've tried to kind of highlight freely available books. Here's another good one where they kind of develop a custom inference system. I've heard it's good. I've never used it. And then here's the big one. If you want to dive deep into how this stuff actually works, read this book. I read it a lot. It's taught me a lot of things. I just want to say thank you for coming and listening and coming out to Monetate. I know Conshohocken probably isn't the easiest for all of you, so I just want to reiterate David's thank you for coming out to Monetate. And like I said, this is a notebook, so if you download these slides, we'll also give you a link to this notebook on GitHub so you can play around with the code. Thanks a lot. Oh, I guess I can do some questions. I filled up just about 45 minutes, but we can do a couple minutes of questions.
By throwing out one or other of the points, flag the outlier.
Yeah, so for outlier detection, if people made methods where you throw away subsets of the points, I'll admit I'm not an expert in this field, but I believe it must be so. That's the answer I'll give. I imagine it must be so. Kind of one of the reasons I like this approach is that it's model-based, so it's a probability model basis for doing that rather than kind of an ad hoc trick that works. Right? It's kind of like, what's one of the big things people lean on for classification and regression is support vector machines, right? They're great, they're computable, they're scalable. One of the few really popular machine learning models that you cannot really express as a generative probability model. Have you tried to pull probabilities out of a support vector classifier? It's hard, and it's hard to do when there's more than one class. Hard to do in a consistent way, right? So in general, kind of when you start to think this way, and I've kind of bent my mind towards this way, you start to prefer things that are probability models for doing stuff like that. So while I'm sure people have done that, kind of my preference is to encode robustness in your prior, or encode when you're thinking about lasso regression. I think about it not as, okay, let's add this penalty term in the L1 norm. Let's add Laplace priors to our regression coefficients, double exponential priors to our regression coefficients, encode sparsity in the prior, encode robustness in your probability model. Is one way of looking at the world. People do plenty of good work, other ways of looking at the world. That's just the way I like to look at it. Any other questions? Yeah. Exactly. You could plug an arbitrary distribution in there, and that's really the point of what I'm trying to get at there. If you think there's one part of your probability model that's wrong, well, so if you're doing this in scikit-learn and you think something's wrong, well, like you better have hoped someone implemented a robust regression in scikit-learn, which that example's simple enough, they may have. My guess would be they probably did. But there's plenty of more complicated models. Just think of like maybe a hierarchical regression model where you want to put a t-distribution on one of the groups to allow robustness there. There's going to be very little off-the-shelf open source software you can do that in, whereas it's a very simple change here. So it's really that flexibility to tell the story of the data first and then change different parts of it that I find very powerful once you see how the model fits. Yeah, you definitely can. You definitely can. You see if it's kind of skewed. And you can go kind of all the way from T to, right? So I talked about one of the examples I gave here that was mine, that's on my blog if you want to look at it, but it's also here, is Dirichlet processes for density estimation. So you could go all the way from normal, kind of the most standard vanilla thing, to T, a little more robust, to a Dirichlet process, so a fully non-parametric error distribution, all by just doing slightly more. Well, the Dirichlet process is actually much more complicated, but all by doing things within that same model and just kind of gradually building up the complexity as you see the data warrants it, which is one flexibility that I really kind of like in this approach to modeling. And now that said, it doesn't scale great always, right? One common thing with Monte Carlo things is they are hard as hell to parallelize. They're really hard to parallelize across cores. Across cores, okay. Across computers where communication is expensive, difficult. That's where some of this more recent research on parallel variational inference comes in. That's much easier to parallelize than some of this stuff. So that's why I also like things that support that. You have a question? I have not. Phil Tatlock, I have not heard of him. Mm-hmm. Yeah, yeah, that's interesting, and it's a there's a connection to some interesting kind of Bayesian methods with prediction markets, which it sounds like that touches on a lot. And a lot of prediction markets got the Brexit wrong, and people who kind of used to be believers in efficient markets are now kind of scratching their heads a little bit, and probably still are going to believe in efficient markets, but have a little explaining to do. Yeah, fair enough. Yeah. Cool. Well, I think I've taken a bunch of time, but please come talk to me if you have other questions. Like David said, would all the Monetate people here raise your hand? If you're interested in what David had to say about Monetate earlier, come talk to me or any of those other ones of my colleagues who were kind enough to stick around till 8 o'clock on a Wednesday night.
Okay, so thanks everyone for showing up. I especially want to thank Corey and Austin for those excellent talks, and I want to thank Monetate for hosting us yet again. If you like to drink beer or hang out with people who are drinking beer, we're probably going to go to, what's the name of it? Conshohocken Brewery. It's like right next door, basically. You go out here, take a left, and walk until you hit a brewery. You can actually walk. Oh, you can walk down the trail. Okay, cool. Or you could just follow the crowd, because I'm sure a number of people will be going there. Also, just wanted to mention, please check the website. We have a number of exciting events coming up this summer. This Tuesday is the hackathon at Candidate, I think. Is that right? I think it's a Candidate. Check the website. It's correct if I'm not. It's about, it involves cancer and, targeting cancer to save lives. I don't know. So who doesn't want to do that? All right. Thanks, everyone, for coming, and I'll see you guys all at the next event.